Welcome back, everyone. In the last couple of videos, we've been talking about indefinite integrals and families of antiderivatives. And a family of antiderivatives represents all the possible antiderivatives of one particular function, because that plus c, that constant, could be any constant you can imagine. Now let's say you want to find a specific antiderivative. Well, with the information we've been working with so far, we would simply not be able to. That's why we have the family of antiderivatives. But if we had a little bit more information, then we could potentially find a specific antiderivative. In these cases where we're given these extra bits of information and are trying to find a specific antiderivative are called initial value problems. Because oftentimes in context, you'll be given the initial position or the initial velocity or the initial acceleration and have to work with that. So let's do an example, and let's say we want to find the antiderivative of the function x minus 2 such that the antiderivative evaluated at 0 is equal to 3. And so that last bit of information there is going to help us to find the specific antiderivative that we're looking for. And using the techniques in the last couple of videos, we know that the antiderivative of x minus 2 will be x squared divided by 2 because I'm using the power rule where I add 1 to the exponent and divide by that exponent. And then minus 2x because negative 2 was a constant, and the derivative of negative 2x is negative 2. And then we add plus c to represent the family of antiderivatives. But we don't just want the family of antiderivatives, we want a specific antiderivative. And this is where that condition that the antiderivative evaluated at 0 is equal to 3 comes in handy. Because even though I don't know what c is, I can still plug in 0 to this antiderivative, and I know what I get out should be equal to 3, because I'm given that initial condition. And so I know that 0 squared divided by 2 minus 2 times 0 plus c is equal to 3. And if I simplify all of that, I'll get that c is equal to 3. So now I know specifically what c is equal to, and so the antiderivative that I was looking for is x squared divided by 2 minus 2x plus 3. And so this is no longer a family of antiderivatives, this is one specific antiderivative that is a function in its own right. Let's do another example that uses slightly different notation. And let's say we want to find the function f of x such that the derivative of f is equal to cosine of x plus sine of x. And we're given that f of 0 is equal to 5. And this is functionally the same problem, except the notation is different in that we're not looking for big F, we're looking for little f, and we're given the derivative function. But relating f and f prime is still taking the antiderivative of f prime. And so we're going to go about it in the same way. And first we're going to take the antiderivative of cosine of x plus sine of x. And from the previous videos we know that the antiderivative of cosine is sine because the derivative of sine is cosine, and the antiderivative of sine is negative cosine. And then add that plus c at the end because right now we have a family of antiderivatives. And just like the last problem, I'm given that initial condition that f of 0 is equal to 5. So let's plug in 0 and set that equal to 5. And I'll get sine of 0, which is 0, and then minus cosine of 0, which is minus 1, and then plus c is equal to 5. And so I'll get negative 1 plus c is equal to 5, and so c is equal to 6. And so the function that we were looking for in this problem was the function sine of x minus cosine of x plus 6, because I now know that c is equal to 6. And so I can get this one specific function that represents this specific antiderivative with this initial condition. And for our last example, we're going to look at an initial value problem which is a little bit more involved. And so let's say you want to find the function f given that the second derivative of f is equal to 4 minus 6x minus 40x cubed, and we're also given that f of 0 is equal to 2 and f prime of 0 is equal to 1. And so the big difference here is that we are not given the derivative but the second derivative. And we need to get all the way back to the original function. And we're also given two initial conditions, not just one. We're given an initial condition for the function f, and also another one for the derivative of f. But overall, the process is about the same. It's just going to take twice as long, because we're going to start with the second derivative, and then first find the first derivative like we did before, and then from there we'll find the original function f. And in starting with the second derivative, to get the first derivative, we still got to take the antiderivative. And the antiderivative of this polynomial, we're going to take it one term at a time. And the antiderivative of 4 is 4x because 4 is a constant. And then for the next term, we're going to have to use the power rule. And so we add 1 to the power, which is 2, and then divide by that power, which is also 2. And for the last term, we're going to use the power rule one more time, and we're going to add 1 to the exponent to give us x to the 4th, and then divide by that exponent, which is 4. And then don't forget the plus c at the end. And now let's use that initial condition, and we're going to use the initial condition that f prime of 0 is equal to 1, because that's what we're looking at right now. We're not looking at f, we're looking at f prime. So if I plug in 0 to f prime, all of the terms with the 0 in them go away, and we know this has to be equal to 1, and so c is equal to 1. And so I know that the first derivative is equal to 4x minus 3x squared minus 10x to the 4th plus 1. And all I did there in this step was I simplified some of the terms. I had 6 divided by 2 to get 3, and I had 40 divided by 4 to get 10. But as always, you do not need to simplify your answers, but it was pretty easy here, so I went ahead and did it anyway. But this is not our answer quite yet, because we were not looking for the first derivative, we were looking for the original function f. So let's make some room here and do the same process again, but we're going to start with the first derivative, take the antiderivative to get f, and then use the initial condition that f of 0 is equal to 2. And for the antiderivative, we're going to go through and use the power rule again. And the antiderivative of that first term is 4 times x squared divided by 2, because I added 1 to the exponent and divided by that exponent. And same thing with the next term, I'm going to add 1 to the power to get 3, and then divide by 3. And then for the third one, the same thing, I add 1 to the power to get 5, and then divide by 5. And the antiderivative of 1 is x, because the derivative of x is 1. And now we have plus c at the end, and now we roughly know what f of x looks like. But we got to figure out what c is, and so we're going to use the initial condition that f of 0 is equal to 2. When I plug in 0 to this, all of the terms that have an x in them go to 0, and I just get left that c is equal to 2. Because the initial condition was f of 0 is equal to 2, and so that's why I set it equal to 2. And so the final answer we get is 2x squared minus x cubed minus 2x to the 5th plus x plus 2. And once again, the coefficients here I got from simplifying the antiderivative above. And one more thing to take note of is that the condition you're given does not always have to be when x is equal to 0. It could be at a different point, and it's the same overall process, just instead of plugging in 0, you plug in whatever you're given. So don't just mindlessly plug in 0, pay attention to the conditions, and then act accordingly to whatever those conditions are.